Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at numbers in different bases. So our system of numbers is base 10. A lot of people think that was invented because we have 10 fingers. So in base 10, we have 10 different symbols from 0 to 9. See, the idea is this: we want to represent infinitely many numbers. We want to represent really, really large numbers like 20 billion and really, really small numbers like 1/10,000,000th of 1. So how are we going to do that? We can't possibly have a different symbol for every single number. So instead what we do is we take our 10 symbols and we arrange them in columns. So you know this already. You know the first column before the decimal point is ones, then tens, hundreds, and thousands. So a number like 3249 in base 10 is 3 thousands plus 2 hundreds plus 4 tens plus 9. So we don't actually need to use base 10. We could change the base. We could change it to something like binary, which is base 2 instead of base 10. So how would that differ? Well, if you're in base 2, you only have 2 symbols, 0 and 1, rather than 10. So if you're in base n, you have n symbols. So how are we going to represent numbers in this base 2 system? We're going to use the same idea as up here. We're still going to arrange them in columns. It's just that the columns, rather than being powers of 10, they will be powers of 2. So this number here, 110011, in base 10, that would be equivalent to 1 2 to the power of 5, which is 32. Then there's one lot of 16, which is 2 to the power of 4, plus a 2 and a 1. So 110011 in binary is the same as the number 51 in base 10. So when we're writing numbers in different bases, we put the base here as a small subscript just to avoid ambiguity. We want to know that this actually isn't the number 110,011 in base 10. So this little 2 just tells us we're in base 2, helps us avoid ambiguity. So these two are equivalent numbers. So there are advantages and disadvantages of each. The advantage of binary is it only uses 2 symbols. That's really good for computers. When they use binary, it's usually like 0 is an off and 1 is an on. But the drawback, the repercussions of using binary, are that you need many more digits to represent the same number. We needed 6 digits in binary to represent a number that only needs 2 digits in base 10. So let's say we start the other way. We're going to start in base 10 now and go to base 2. So we've got the number 832. So if a base isn't written, you can assume that it is base 10. So I want to write this in binary. So what I have to do is write 832 as the sum of powers of 2. So start with the highest power of 2 less than 832. So that is 512. So for 512, I need to add 320 to get to 832. Of course, 320 isn't a power of 2. So I'm going to write 320 as the sum of powers of 2. So it is 256 plus 64. So I've written 832 as the sum of powers of 2. So I put a 1 in the 512 column, a 1 in the 256 column. The next column's 128. I didn't have any of those. I had a 64, no 32s, no 16s, no 8s, no 4s, no 2s, and no 1s. So this is the number in binary, 110, 100, 0000. So this number here, 832, is larger than 512. The highest power of 2 less than 832 is 2 to the power of 9. So this has 10 digits. Just as in our normal base 10, a number that's between 10 to the power of 15 and 10 to the power of 16 would have 16 digits. All right, let's now look at another base. So let's now look at hexadecimal, which is base 16. Computers actually use this for certain tasks, one of which is representing colors. So in computers, they represent colors with a 6-digit code. The first two tell you how much red to use, the next two how much green, and the last two how much blue to use. So we're going to convert this to base 10 in a second. We're not treating this as one big number though. We're treating one number for red, one number for green, and one number for blue. So in hexadecimal, you get these weird letters as part of numbers. What does that mean? Well, the problem is in base 16, you need 16 symbols. So if we go from 0 to 9, we only have 10 symbols. How are we going to represent the number 10? Well, we can't just write a 10 like this, 1, 0, because that can become a bit ambiguous. Is this the number 10 or is this the number 1, 0? Because in base 16, 1, 0 means 16 plus 0, or 16. That's how you represent the number 16. So we can't use that. So to represent a number like 10, they've just decided that we'll use an A instead. And then B is 11, C is 12, 13, 14, 15, and so on. So similar to the discussion, we looked at the advantages and disadvantages of binary. Hexadecimal has the advantage that if you're storing digits, you need fewer digits in base 16 to represent a number than you would in base 10. But of course, the disadvantage is you need more symbols. So sometimes one advantage will outweigh the disadvantage or vice versa. So let's look at this code here that actually codes for one of my favorite colors. It's this bright turquoise color. So we'll just look at the first two digits and convert that to base 10. So there's a 1 in the 16s column and a 2 in the 1s column. So this number 1, 2 in base 16 actually corresponds to the number 18 in base 10. What would the number FE represent? Well, F we know is the symbol 15, E is the symbol 14. This is the number 15 16, so 15 times 16 plus 14. That actually gives us the number 254 in base 10. So you can see here we need 3 digits in base 10, but only 2 digits in base 16. And then this last one here, so D is the number 13. So this number here would be 13 times 16, which is 208, plus 8. This number D8 represents the number 216 in base 10. So the code for this color would have a little bit of red, a lot of green, and a lot of blue. So the highest 2-digit number in base 16 would be FF, which is 255. It's one less than 16 to the power 2, which is 256. So this one has almost maximum green, quite a lot of blue, and then not a lot of red, because you can only represent colors in the computer using 2 digits for each color, 2 for red, 2 for green, 2 for blue, and the highest 2-digit number you can have in base 16 is equivalent to 255 in base 10. All right, how are we going to go the other way? Let's convert 1,000 into a base 16 number. So again, if no base is written, you can assume it's base 10. So we want to write this as the sum of powers of 16. So what we're doing here is kind of like what we did in the Euclidean algorithm. So we're going to start with the highest power of 16 less than 1,000, which is 256. So 1,000 is 3 times 256, which is 768, plus 232. So now we're going to write 232 as the sum of powers of 16. So 16 goes into 232 14 times. 14 times 16 is 224, so there are 8 left over. So then we just have 8 in the ones column. So this number 1,000, we need 3 in the 256 column, 14 in the 16s column, and 8 in the ones column. So we have 8 in the ones column. Now to write 14 in the 16s column, remember 14 corresponds to this number here, E. So we put an E in the 16s column, and then we put a 3 in the 256 column. So we've written 1,000 as 3 lots of 256, 14 lots of 16 plus 8 lots of 1. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.